Hi, so officially you're welcome to another session of our PLD discussion. And in today's session, we are discussing dynamic memory allocation. Dynamic memory allocation in C. Maybe quite controversial if you don't understand it, but if you understand it, it's not that controversial. And I keep saying that anytime that a new concept is introduced to you, you should be interested in what it is, why you need to know it, and when you use that. Okay, so in this our case, we should be interested in what is this dynamic memory allocation at all. Why do we need to know about dynamic memory allocation? When do we even use it, and how is that used? Okay, but before I talk about any of those things, there are some basic stuff that I believe when you understand, it makes the understanding of the whole dynamic memory allocation concept easier. Okay, what do I mean? Right now, almost every one of us have used a computer before. I want to believe that. I don't know how you would have been to this state without ever using a computer. So you all used a computer before, and on your computer, you store files on your computer. So if you have any documents at all, you've created a document or you downloaded a software or you have pictures of yourself, all of those things are files, okay? So one thing that we should know and be aware of is that there is a storage device in your computer. A storage device in your computer. And this is what we commonly known as our hard disk, okay? So commonly we use the hard disk as a storage device in the computer. There are different types, but that is not for us to discuss right now. All I need us to understand is that to be able to store the images, the videos, and all the other things, files that you have on your computer, you need a storage space, okay? And in your computer, you are using something in the form of a hard disk. All right. But aside the hard disk, there is also something for memory storage, okay, which we need to understand. And in case of our computer, we are using what we call the RAM. That's a random access memory, okay? And if you've ever been privileged to see the inside of the computer, that is a computer that has been opened, you probably would have seen this memory. Usually just a flat card like that, green in color with some brushes at the edge with some demarcations on it, okay? So that happens to be the RAM. If you've not seen some before, after this discussion, just Google RAM and see how it looks like, okay? But basically, that is what most of the things that happen in your computer, okay? That's where they happen. The processes that take place in a computer, that's where they happen. So now let's bring it to our C program. When you create your C files, okay, so you created maybe main.c, you created main.h, and many other files that you create. All of these things are files. And for the time being, as you are creating them, they are being stored on the hard disk. Guess what? So the files that you are creating, now if I go into my computer and I create a new file, it's being stored automatically, or you have chosen the location on your hard disk that you are going to store it. Okay, and if you know, your hard disk can be divided into several directories. So you could have had, in fact, by default, there are a number of directories in there. You could have downloads directory, you could have desktop, you could have user directory, and a lot of directories together with subdirectories. But we are not concerned with that. All we need to know is that the files that we are creating are being stored on the hard disk. But the moment we want to run a program, this is what happens. When you want to run a program, so these files, if we want to do a C program, what do? We are going to compile these files into probably just a single file known as a.out. Okay, or it could be anything. We could call it anything. App, we could have app.exe, all right, or any name that we give it. Now we know that let's take to a.out, okay, a.out. So that is the specific file for our program. So assuming you've written a program that does addition or any function, place any row at all, and the program has been compiled into an a.out file. So far as your program remains on your hard disk, somewhere in your hard disk, maybe in the downloads directory within the hard disk, you have the a.out file. It is still known as a program. Okay, but the moment you are going to run it, when you are about to run the program, this file will be moved to the memory. So the computer's the processor picks the data from the memory. The processor doesn't go to the hard disk to go and interact with the hard disk. It picks the data from the memory. Okay, so that means that before you run any program, there will be a part of the program that will be moved to the memory. Once in the memory, the computer's processor can get access to it and use it randomly. Please, let's understand that concept. So if I want to run this program that I've written called a.out, before I run it, my computer will automatically move this program into the RAM. That means that it's going to create space for it in the RAM. Remember that the RAM is memory, okay? And if you are using a machine like what I'm using right now, you probably have, say, 8 gig of RAM, or you have 4 gig of RAM, or 16 gig of RAM, or any size of RAM at all that you could have. But what happens is that it is a finite space. It is a finite space. And if it is a finite space, that means that at one point in time, you can run out of memory. So the good thing about C and programming in C is that it teaches you to appreciate how this memory is used, so that you are able to write efficient programs, or you are able to make your code run efficiently, or make good use of the memory. You don't just play around with memory. Okay, so please, is anyone unmuted? Hi. Okay, sorry. All right, so what I'm saying is that let's understand these basics even before we get into the memory allocation itself. Okay, the thing is, you have a hard disk that stores, like, if I could say, the hard files themselves. So the file that you created, where it's stored is the hard disk. But for the program to run, you need to move it into, you don't do it. Like, the computer knows how to move them, when to move them. Okay, so the computer moves it, the program files to the memory. Then, so far as we have been able to move it to the memory, it is now termed a process. So the computer is doing what? Is processing all those data in your program. So that is termed as a process. So if you ever open your task manager, you get to see a number of processes are running concurrently. This means that the files related to all these processes have been moved from the hard disk onto the RAM, or the random access memory. Okay, and what I was saying was that your RAM has a finite size. So someone may be using 1 gig of RAM, Another person may be using 2 gig of RAM. So recently, I've heard a number of people complaining about their phones giving them issues after they started working around dynamic memory allocation. The problem is that the memory we are dealing with right now is finite, like it has an end. So if you use up the 1 gig that you have, then you have exceeded the memory that you have, and you won't be able to run other processes. And in fact, some other processes even require that there is extra memory for them to even work. Without the extra memory, they are not going to work. So you see a number of your processes will be crashing. But sometimes you have in your phone, right now as I have my phone, I've not opened it, and you think that nothing is happening. But in the background, there are background processes that are running to keep the phone on. Because one, for instance, the internet access is on. So people who are sending me messages are coming through, even though I've locked the phone. Okay, and the only reason is that there are background processes. Okay, so all of these processes that go on in a device happen in the memory of the device. The point I'm making here is that we should remember that the memory that we have is a finite memory, and that means we can use like everything. We can exhaust every memory that we have there. And by now, this 1 gig, 2 gig, 4 gig shouldn't be mysteries to you, okay? Because we've learned about sizes of stuff that we work with. So you know the size of a character, you know the size of an integer. So if you have, let's assume a character, you have one character is 1 byte. Okay, 1 character is 1 byte. Now you ask yourself, how many bytes make a gig? Okay, or a gigabyte. So if you know the number of bytes that make a gigabyte, it means that if your program expects, let's say you have only 1 gig of RAM, and your program is using up that number of characters at a go, then you know obviously you are going to exhaust that 1 gig of memory that you have. So as a programmer, let me use the right thing. As a software engineer who understands this memory allocation stuff, you'll be able to build your program such that it makes good use of the memory. And I'm pretty sure if any of us have installed a program before, you realize that most of the programs, when you are going to install, they tell you a minimum memory size that it is required for the program to run. So a program, when you want to install it, will tell you that, for this program, you need a minimum of, say, 2 gig RAM for this program to run. That means that the program may be using up to about 2 gig RAM at its peak performance. Okay, so very important, and hopefully that part makes sense now. You have a RAM that has a finite size. Okay, so anytime you are going to run a program, the program is moved to the RAM, like a space is created in the RAM for the program to run. But another important thing that we need to understand is that inside this memory that we have, the memory has been divided into different parts, and each of the parts accommodates different parts of our program. So now let's come to C program that we have written called A.out. We are going to run this program, and by now you and I should know that a C program has different parts. So for instance, let me open the online compiler and use that for an example. If we open this compiler, yes, so here we have something like the comments. You come to this as main function, okay, and we could do other things, like we could declare variables, we could create more functions, and the like. So that tells you that your C program has a lot of parts. And what I'm saying right now is that for each program, there are different parts in memory. They are not all stored in the same space. So the memory has been put into different parts. So let's do a representation here. Say this is how the memory has been shaped. Okay, so the first part, one thing that you should know is that even with this one that we are going to be using, it's not like the complete thing, but the one that we need to know and work with, the one that we need to understand and work with. Okay, because some of them we do not control them. Once you cannot control it, even if you know it, it doesn't change anything. Okay, so that is what we should know. So the first part is usually known as the test segment. The test segment. And with the test segment, what happens is that the program itself, this our A.O program, okay, you remember that this is just compiled code. There is compiled code in it. So essentially, it is like the machine code that is in there. So the first thing that will happen is this was being stored. Maybe you created a directory, just as we always do when we are working on these programs. We create probably a repo, then inside the repo, we create a directory. Okay, so in your hard disk, you have created a directory that contains this file. For you to run the program, the first thing is that the file containing the code is moved down into the test segment. So when you go to the memory, the RAM of your computer, the test segment part of your computer is what is going to take up the A.O. That is the file containing the code that you have written or the program that you have compiled. Is going to be stored in the A.O. But the moment the program itself begins to run, there are a lot of other things that are needed, a lot of other parts of the memories that will be used. Okay, so the next thing is known as the data segment. The data segment, and with the data segment, is usually divided into two parts. So the data segment is divided into two parts. But the question is, what is stored in the data segment? Your program comes, depending on the program that you write, okay, it may come with some data that will be stored here. An example is what we call static variables. So if you ever create a static variable, it will be stored in the data segment. If you have a global variable, that will also be stored in the data segment. The static variables and the global variables will be stored in the data segment, okay? But the data segment is divided into two, as I said. Usually we have the initialized and uninitialized, okay? So uninitialized variables. Please. Sorry. Okay, then we have the initialized variables. Okay, but these ones are coming from the static and the global. All right, so for the ALX program, please give me a second. Okay. Yeah, sorry. So for the ALX program, I think we are here to talk extensively about this, okay? But what happens is that if inside this my program, if I go ahead and declare, say, a variable here, say, or assign a variable here, what I've done here is I've declared a global variable, okay? A global variable. And the reason why we say it's a global variable is because this variable that we have, we didn't declare it inside main. This means that if I come and create another function called sum, this sum function should be able to also use the same variable that I have. without necessarily calling main or having to call some in main before I use it. Okay, so a global variable is like a variable that is available to every part of our code. In fact, we should, I don't know if when you are reading on variables, you read on the scope of variables, but that is where they fall in. And unfortunately, that's not a focus of today's lesson. But I just need you to say this, okay? So this is one of them. And that kind of variable, either a static variable, I think static variable will cover it later. Static variable or global variable, they will be stored here. So in that particular example, our x is equal to 10 will be stored here at the part that has been dedicated for initialized variables, okay, in the data segment. Now, beyond these two segments, we go into the parts that our program actually will use up then, especially when we are running the program, okay? So we now have what we call the heap segments, and a stack segment up here, okay? And what happens is that this is memory. And I've told you, let's say you have 4 gig of memory. Let's assume that your memory is 4 gig, okay? So the test segment will take some size, the data segment will take up some size, the stack segment, the size that the stack segment will take is dependent on the program that you've written, okay? But it's kind of phased. It's kind of phased because when you write your program, the stack is like the various functions that you write, the local variables inside each of the functions, the space, how much space are they going to take up? Okay, those ones form part of the stack. So after you have written your program, we can calculate and tell that for this program, this particular function will take this size, these variables, all these variables will take this size. So at the end of the day, your computer is able to detect how much space to give to the stack. Okay, so you will have, let's say, this space allocated to the stack. In fact, there is something up here, like, just as I said, some of these things are just summarized for us to understand, and the ones that are important to us, okay? So I think our last discussion, we talked about command line arguments. So there is actually a space for command line arguments in the memory. So those ones will be stored in this session. In fact, right now, with what we are going to learn, we don't even need to consider this, that. Now, stack, as I've said, is for the functions and the local variables that we declare. So any variable that you declare in main function would take up space in here. So you learned that if you come here and do say y is equal to, then pass, let's say this. This variable is definitely going to take space, and since it is a character, we expect that it takes up 1 byte of space. That means that there's going to be a main stack, okay, or a stack frame. So the main function will have its space, unique space within a stack. Then that main, inside the main, you declare a variable. So within that stack, we'll have the variables that we have declared. The local variables will have their spaces there. So that's why it was important for us to learn about the size of character, the size of integer, double, and co. Because when they go into the stack of the memory or the RAM, they take up that much space. So all the functions that we define will take up space one after the other until we, I think I tried to do an example. I'll explain it further, but let's get the basic concept, okay? So one thing is that if main calls another function, that function will get its fragment sort of. Okay, then if that function, if there is a call to another function, so you realize that the stack is always going down. It's taking out space downwards. Okay, then when that particular function is done executing, we lose it. So that memory that it took away or kept to itself, once it is done executing, we would replace that memory. Like we no longer use that memory. All right. Now the last and most important bit that we need to know is this other portion known as the heap of the memory. Okay, the heap. And what a heap does is that it is a memory that is available to us. So now anything that you want to do, you realize that with a stack memory, you would have to know the size. In fact, you would have to like automatically determine, when I say automatically, it is automatically determined. Okay, so it's like for the memory that our stack is going to use is fixed. But when we come to the heap, that is when there is that flexibility. Now we have the flexibility to choose how much space we want to reserve. In fact, it's like the rest of the space is available for us to use. So far as it is there, we are available to use it. And what happens is that a heap also grows like this. So maybe you start by creating or using up one space, then another space, then another. So the heap goes upwards like that. Okay, so as your program is running, you could have a number of functions executing. Imagine if you give a recursion without a base case, a recursion that keeps on recursing. It's going to be creating, that is in the stack because it's a function we are talking about. So this function has created or taken up one fragment like that, another one, another one, another one. It will keep using up the space in the stack. Then if you are also having a program, inside your program, you are using the heap memory as well, then eventually what is going to happen is that this will come to meet up with this. So that is where you would have used up all the memory that you have. Once you exhaust that memory, some of your processes won't run, or your program may end up crashing. So that is the practicality of it. And that is what we need to know before we can understand the concept of dynamic memory allocation. So let me try and take it again in order for you to understand it. So I've said that if you have a program that you have created and compiled that program called a.out, after compiling it, this program is existing somewhere on your hard disk. But if you are going to run it, then the computer has to move this into the RAM. So it has to move it into RAM so that the processor of the computer can have access to it and run it. In fact, it applies to every program that you run on your computer. The original file, the executable file, is lying somewhere in your hard disk. But for the computer to use it and run the program, give you the outcome you are looking for, it has to move that executable file to the RAM. Once it is inside the RAM, the processor can have access to it and use it anyhow it is supposed to use it. But what we need to understand is that the RAM as we have it has actually been divided into different parts because the programs that we write also contain different parts. And each of the parts use memory differently. It is that simple. The program you've written contains different parts. These parts use memory differently. So all you need to know is which part of the memory does this even go to? Which part of the memory does this even go to? That is what we are interested in. So to begin with, we talk about the test segment. Okay. So with the test segment, we are saying that this final project or program that is executable file that you have compiled will be moved into the test segment. So it means that if or until this program is moved here, you can't have your program running. So that's the very first thing that will happen. Your computer knows once you click on this or you run it, usually in Linux systems, you run it with the /, then the name of the program. Once you do this, okay, your computer knows the location of this file. So it will go and pick this file and put it into the test segment of its memory. Once in here, the next thing your computer looks for is what are the data variables. Let me put them inside the data segment. And I mentioned that with the data segment, they are usually divided into two. We have the initialized and uninitialized. In fact, I don't think they are important to us right now. Okay, well, all we need to know is that those global variables, those static variables that we are going to end up declaring, they are going to be stored in the data segment. So at the end of the day, we are going to have some memory occupied here as well as here. We don't need to concern ourselves with it. If our program has some command line arguments, and we discussed command line arguments the last time. So if our program has some command line arguments, we will have them here. So there is space for them as well. And you should remember that even if your program doesn't have a command line argument, as you may think, the name of the program itself is a command line argument. So that means that something will definitely be inside this space. Now, our interest is not this, nor this, nor this. Our interest is with these two. The rest of the memory that is left. But the unfortunate thing too is that when it comes to the upper part, which we call the stack, so the stack segment is also not really available like that. We don't regulate how the stack is used. And it is automatically determined based on the code that you have written. So the stack is meant for the various functions and the local variables that you create. Functions and local variables that you create. So your program will automatically allocate all of these. Once it sees a function, if you are going to call the function, it's going to create what we call a stack frame for that function. So say the first one, the point of entry to every C program is the main function. So the very first one it does is to allocate space for the main function. So this becomes the main function stack or stack frame. Okay, the main function stack frame. So that stack frame is left for the main function and its local variables. Those will take up that space. Then if there is a call to another function, we would now dedicate another stack frame to that new function. If there is another function, we will dedicate another space. Okay, so as your program is going to run, your computer can determine how many functions do you have in this program. When and when are you going to call it? How much space do I need for this stack? Okay, so at the end of the day, we realize that there is a phased allocation of space for the stack. For that matter, we call that space the static memory. It is static because it is phased. And it is phased because you have written the program. The logic is there. The computer will see, okay, this is the logic of this program. It's going to call this function, store this variable, call this other function, store this other variable. In fact, they have about 10 variables. They have 12 functions that I'm going to call at a row. And all of these will amount to this size. So let me allocate that size for the stack. So I have a phased memory allocated to the stack. Now, I have this other memory that is left for me to use, so that any other thing that I can't predict beforehand, the size, or I want to take control of where exactly it is located, then I come into the heap. Okay? So the heap is where we have dynamic memory. It is dynamic because here we can create a space for something. We can remove it when we want. We create it, we remove it. So you decide that, okay, inside the heap, I want to create like space for about 4 different stuff or about 200 different stuff. I am going to create them, and when I want is when I remove them. So that becomes dynamic. For the static, we didn't have that control. The computer was automatically doing that for us. So all we needed to do is present our code to the computer. The computer knows what to put at the test segment. It knows what to put at the data segment. It knows what to put at the static, the command line arguments aside as well. But when it comes to the heap, we have absolute control. What do you want to put there? So you decide that, okay, I'm going to put so and so in this heap. Afterwards, I'll create another thing. So the space is available. And remember that this space, as I have said, is a finite space because your memory has its limits. If you are using a 1 gig RAM and I'm using a 32 gig RAM, we can't all run the same set of programs. So sometimes you would open like 12 different applications on your computer and realize that they start crashing. So the problem is that now all these programs that you've opened have created processes that are running and they need to use up this space. Depending on how each of the programs were written, you may be using up the stack memory as well as the heap memory. So if you eventually end up consuming all the memory, now there is no space for any other process to run. Therefore, your program begins to crash. I hope that explains the basis. Let me pause here and take questions before we can move on. Yes, questions? Yes. No one has a question? All you people can hear me. Everyone is fine. Is that it?
Yes, yes.
Okay.
I heard you clearly.
Okay, that's good. It is good to know that everyone had it. So now we can move on. All right. So as we have discussed, now when we talk about dynamic memory allocation, it means that we are zooming into a specific part of that frame or segment that I drew. Okay. So we are zooming into a specific part of our memory. Here, we would have to try and consult our imaginative, I don't know, nature
Hello,
or something.
doctor.
Yeah, hi.
Sorry, I have a question. And
Okay.
the question is, assuming that I opened a Chrome browser now,
Mm-hmm.
I'm browsing with a Chrome now. Assuming
Okay.
that it's like we are executing that Chrome as a program written,
Yeah, yeah.
and it has loaded the function for the Chrome, this and that, all those cache memory and likes on our memory. Can we assume that maybe I want to open Microsoft Word or I want to play music using VLC? Can we assume that the rest of our heap memory remaining on our RAM is the one that another program we use to load? Or how can we say what other RAM, let me put it
Okay.
like, how can another program, where can they, which RAM would they use?
Yeah. Yeah, I get it.
I think you get my point now.
Yeah, I get it. All
Okay,
right.
okay, sir.
So the answer to the question is that even though we've drawn just this segment, this segment that we have, like this frame for the representation, is just to explain the concept for us to understand. Okay. It's not so as you have opened the, how do you call it, the Chrome, the computer knows exactly which part of its memory to keep it. It doesn't mean that when you open Chrome, let's take the very first part, the test segment. Okay, there's definitely more room. Let's assume you are using a 4 gig RAM machine. So there is space for this, and that means that your Chrome file, so say chrome.exe, would be put here. If you go ahead and open, say, word.exe, there's still space for it in here.
Okay,
So it will
okay,
not be taken to heap. There
okay,
this is just a representation to explain what is happening. But the computer knows exactly where to put what file. Okay.
okay,
But the moment where you have exhausted every memory that is allocated to the test segment, or
okay,
the moment where your program has exhausted the whole stack and the whole heap, you have
oh,
exhausted every bit of the memory, then you can't run any other program.
okay, okay,
But if you are going to run a program and there is space for each of these things, if there are command line argument, there is space for it, there is space for the data segment, there is space for stack, there is still room for heap, then that program is going to run and execute everything that it does. It's going to do it perfectly. But the moment you consume all the memory, so if you have programs that are running and all of them put together, the processes have consumed beyond the 4 gig, then you have
okay,
no room to accept any other program. For that
good,
matter, it's not going to run.
good, good.
All right.
Can we know, I mean, a user, is there a, maybe a command to know the actual memory allocation for the text segments?
Okay. So I think I not every bit of them, but I think there is. Let me reflect. So, mm, let's try something, but we'll probably have to do research. Maybe there is an easier way. In fact, if you are using a computer, a Windows machine, you can use a task manager to check that. But for the program that you create, you can have an idea of, say, okay, let me choose this and see. You can have an idea of, say, how much space is this going to take up, sort of. Okay,
Okay,
let's see the progress. This is A. All right. So if I do size A, if I do size A, it gives me an idea of the sizes this program is taking. Okay, so 2,351 bytes for the test segments.
okay, okay,
Then 648 for the data segment. So, like some of them, you have an idea. In fact, you can even go and check the size of your file, just like you do for any file at all. You get to know that, oh, this file is 1 megabyte, like the
okay,
executable file is 1 megabyte. Okay, but
okay,
the memory usage itself, I don't know much about that. However, if you are using a Windows machine, you can check the processes and see how much they are consuming, and it will give you an idea of what is happening. Okay,
okay. Thank you, sir.
but you're welcome. Pretty soon, we are going to be learning some stuff about data structures. Data structures, where we are going to learn how to efficiently use these things. Okay, all the programs that the concept that we've been learning. How do we use them so that we maximize the use of the space? So I think that's an advantage to learning a programming language like C, because then it opens your eye to the actual things that are happening inside your computer. Now you know that, oh, so when I'm doing this thing, this is what is happening in my computer. So for those of you who have ever tried it before, you run an unending while loop, a while loop that is not terminated. You realize that your computer ends up crashing because it's going to keep running, keep running, keep running. That means that the space that is allocated is going to use up all the space that is left in your computer and essentially crash. Okay, and in fact, a number of things, if you write a recursive function that does not have a terminating case, it will run like that. So that means you're going to use up all the space that is left on your memory, and your computer is going to end up crashing. And I feel that almost everyone would have had a similar experience where you were doing something, your computer just froze, or your computer just crashed and it went off, something like that. The computer had to force reboot itself. Okay, so all those things come in, and that is what you do when programs are written by unexperienced software engineers, people who don't have any idea about these things, especially the data structures as we'll be learning. So they are just doing anything at all. Oh, I'm a programmer or I'm a coder, I just put codes together. But you don't understand all these behind the scenes stuff that is happening. Okay, so that's the essence of us learning about C. All right, so hopefully we are getting the gist on this. I want to focus this session on the explanations, okay, so that in the next session then we'll do more of the practice for you to see how we do all of those dynamic allocation stuff. But for now, with what we have learned, you should realize that is the heap segment that is of interest to us if we want to dynamically allocate space that we can control. It is a heap segment that we would have to be playing with. Okay, so we are going to zoom into just that part. This means that almost everything that we have learned so far comes into play. If I ask you what is the size of a character, you should be able to tell me. Because if you are going to create a space or you are going to put, let's say, a variable, you decide to go and put that variable in the heap, then you should know the size that it's going to take. And in fact, because the heap has that memory, it allows us to create storage spaces for the arrays that we are going to create, okay, and structures or structs in C. So if you are going to create a struct, you are going to create an array. So make it flexible enough for you to work with, okay, because you want to be able to add onto your array, you want to be able to delete from your array and then likes. Once you want to be able to work or operate on these your, I can't call them objects, but I mean the structures containing some data that you have saved. If you want to be able to operate on them as your program is running, so during runtime, you want to operate on them, then we should be looking at the heap memory. If you create an array inside the stack memory, you can't change the size of that array. If you create an array inside the stack, I mean, when the program is already running, there's no way you'll be able to change the memory of that program or the size of that array. Okay, but if you are working with the heap memory, then you are able to change it. So assuming that you created an array to contain a set number of things, after some period you are going to add another set of numbers to it. Such an array should be stored in the heap memory and not the stack memory, because once you leave it in the stack memory, that size is fixed. The computer will automatically calculate, okay, this array is this size, is going to take characters. So if it is 4 members, 4 times 1 byte. So we have 4 bytes that is going to be stored for that array. But if we use the heap, then along the line, we can decide to change the size. We can decide to add on, we can decide to take away from the size that we have given. But we can even decide to delete it when we want. For the stack, one difference between the stack and the heap is that for the stack, as soon as the function is done, you are going to lose that memory. As soon as the function is done, automatically that memory will be wiped off. So if your computer reserved some space for a function that you created, as soon as it's done executing, it will wipe that space away. So that frame, the stack frame that is allocated to that function will be wiped off. So by the time the whole program is done running, everything within your stack is automatically wiped off. By the time the whole program is done running, your stack will be wiped off. But for the heap, you manipulate it. So you decide that, okay, now I'm done, therefore let me delete it. Or now I want to add on, so let me add on. Yes, Ima?
Doc, sorry for interrupting. How do we then know the actual memory location that we are working on?
Well, what do you mean by the actual, whether you are in the stack or you are in the heap? Is that a question?
Yes. Yeah.
Okay, so now that that's what we are learning, that for the functions, for the local variables, they are in the stack automatically. But the things that we are coming to learn today are what you use to go into the heap. So until you have chosen any of these things and gone to the heap, you are not using the heap. So for the heap, you decide when you want to go and use it. You decide when you want to unuse it. Okay, so it takes you doing something. So if I want to use up some memory in the heap, I have to do something before I see that, okay, now I am in the heap. If I have not done anything of that sort, then I am not using the heap. Yes, I don't know who else on it. Hi, Steven.
I want to, yeah.
Okay.
Is there anything like a garbage collection in C?
There's
nothing like garbage collection. What if we create a program without using malloc or pointers? How are the memory managed? The memories of the computer, how is it managed in that case?
So if you are writing a program like that, basically I think you are not using up the heap. So at the end of the day, it is a stack frame that your program is going to use mainly. And what we know about the stack is that it automatically clears itself so far as you are done using it. So it's not going to keep them and cause a problem. Once that function is done, once that local variable scope is over, we'll just trash it, remove it. So for the stack, that is automatic.
Yeah, usually, the garbage collector takes care of this in other languages. But I don't know it happens in C. Like,
I don't know about that.
Okay. All right. I'll find out.
Okay. So I don't know about that, but once you brought it up, I would also equally try and look around it and see. But for now, what we need to know is that with the stack memory, if you are not using the heap, in fact, you shouldn't even worry yourself much about the stack memory. Okay, just that the only reason why you worry yourself about it is you want to make good use of it, because just as I said, when we start talking about data structures and algorithm, we will learn how to make approach efficient or choose the best way to get a problem solved. Okay, but aside that, every time that we are using the stack, the computer does the work itself. He knows that, okay, now you need a new frame, so let me give you that frame. Now you've exhausted this frame or you are done using it. So let me wipe it. Okay. But when you use your heap, if you don't clean it, it will be there until you clean it. But one thing that we should also know about our RAM is that with a RAM, when there is power outage, I mean, it is temporal. Everything on the RAM is temporal. So if I put my computer off and I put it on again, the things on the RAM will be wiped off. So that's why when your computer froze or crashed, you're able to put it off and put it on, and the computer restarted and was working. Even though before then it wasn't working because some processes had used up the whole memory. Okay, so the RAM is such that it is temporal. So far as there is power in your computer, it is running. But as soon as power goes off, you lose everything in the RAM. They all go back to where they came from. So it is a hard disk that is doing the actual storage. But to make a process work, we have to move it from the hard disk onto the RAM. And during the process, when we are actually working on the RAM, that is when we put that is where our computer is able to access it. If by chance we happen to overuse the RAM, the computer may end up freezing or giving us some unwanted behaviors. And if it happens like that, maybe it's frozen, it's not responding, all of that. One of the easiest ways is just turn it off and turn it back on. What happens is that when you turn it off, you clear the RAM. When you turn it back on, any other process that is supposed to run at startup is what is going to go back onto the RAM. So if the program that was giving you the problem is supposed to run at startup, then when you turn it on, it will automatically come back again and come and cause that problem. Okay, so at least that gives us a fair idea of what happens in the RAM of our computer. But now our interest is in the heap segment. What happens there? How do we create space for what we want to do? But if you remember when we were talking about pointers, I made a point that pointers, as we know, are just kind of special variables that point us in the direction of other values or variables. So why at all would it even be necessary? Since I already have a variable. So I have a variable, I've declared a variable A equal to 4, maybe an integer variable. Then I now come and declare an integer pointer called PTA and say this is equal to the address of A. Why is this necessary? Because I can always call A and get 4. And I mentioned that in later times we'll learn about dynamic memory allocation. Without pointers, you can't do dynamic memory allocation. Without pointers. So, in essence, you may feel that you could have done any other thing without pointers. In fact, it has other advantages. And we have looked at that using passing pointers to functions or passing by reference, as we call it. We have looked at those other advantages of pointers. But this is the key one. Without pointers, we can't manipulate the memory. So that means that you can't be a good C programmer without understanding the concept of pointers. So if you are forgotten, then you want to go back and go and read on pointers, try and practice them, because without them, we can't do dynamic memory allocation. So now to dynamic memory allocation, there are a number of functions that helps us dynamic memory. There are a number of functions that helps us do this dynamic memory allocation. The most common one that we are going to be talking about is malloc. Okay, So that's memory allocation. We have alloc. Then there is realloc. Okay. Then I think there is the last bit that we may have to also talk about, free. So if you understand this, you practically will understand the rest. That is what you should focus on. Once you understand what malloc is and how to use it, you practically understand the rest. So hopefully in the next session, we'll take specific examples. Okay, we'll take specific examples of this malloc, how it is done practically or how we use it practically to do that. Okay, but what happens is that anytime you call malloc, the argument that you are supposed to pass to malloc is the size of memory in bytes. So size of memory in bytes that you want to allocate all the time. Tell us, how much space should we give you? In fact, I can give myself 1 gig. So imagine going to give yourself 4 gig when you are using a RAM of only 1 gig. Imagine what is going to happen. But anyway, we'll talk about what will happen later. So what happens is that whenever you call malloc, okay, your argument of interest is the size that you are going to allocate. So just by saying, hey, malloc, then say malloc 10. Let's just say this, malloc 10. Just by doing this, I am creating like a space for 10 bytes. I'm creating a space for 10 bytes, okay? And you should know by now that when we talk about the memory itself, and how data is represented in the memory, it's actually in a contiguous form. So it is in this kind of straight line form. Sorry for my zigzag line. Okay, so if I'm going to reserve 10 bytes, then this will be, let's say 1 byte, 2 byte, 3, 4, 5, 6, 7, 8, 9, 10. Do I really have 10? So say this is 1 byte 2. We are programmers, so we should learn to count from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so this malloc as I've called would go and keep this space for me. Okay, so from here to here, that's what a malloc is going to do for me. I should be able to have access to it. Okay, but one thing you realize is that what type of data is in here? What type of data? And how do I even access this? Once they are in order, okay, once they are in a contiguous order, all that you should be interested in is the first one. If I give you the address of the very first one, you should be able to access any of these. I hope you understand that concept. Once you know that, oh, I allocated space for 10 things, okay? Let's say I allocated 10 bytes, and so each of these is 1 byte. All that I need is what is the address for the very first one. So if the first one's address is ending in, say, 80, then it means the next one will be 81, 82, 83, 84, in that order. So it becomes easy when I know the address of the very first one. Then, what do we use to store addresses? if you remember, we use pointers to store addresses. That means that I can create a pointer that points to just this one. Once I have a pointer that points to just this one, I'll be able to access any of these with that particular pointer using pointer arithmetic. Or, because they are in a form of an array, we can use those array subscripts to get the subsequent values or the data in these specific spaces that we have allocated. I hope it is making sense. Let me take that again. So if you go ahead and say malloc 4, all that you have done is that inside the heap segment, I want to store 4 bytes of space. Okay, so the actual representation in the memory looks like this. It is just a straight thing, and we have 1 byte each. So this is 0, 1, 2, and 3. So malloc 4 is going to store this space for us. That means that this has been stored in the heap segment, and we can use it for anything that we want. Then how do we make use of this? Well, since they are in a continuous order, as I said initially, all that we need to know is the address of the first one. Once you have the address of the first one, we can always access every other one of the spaces that we created. So far as we have the address, and we have already learned that to store an address, we can create a special variable called a pointer to store an address. This means that whenever we are going to call malloc, we should assign malloc to a pointer, because malloc is going to return the address to just this one. So this function, malloc function, is like the person who wrote the function itself says that this is going to return an address to an empty space, depending on the size that you have created. So the very first one here is an empty space for malloc. Okay, it's an empty space. So that is what is going to happen. So you realize that they say it returns a void pointer. Okay, so that is how the prototype of malloc looks like. This is how the prototype of malloc looks like. It tells you that malloc will always return an address. An address to what type of data? We don't have a specific type of data. In fact, it could be anything. So we say it is a void pointer. It returns a void pointer. But our point of interest is the fact that it is returning an address to the very first element, or index 0. That is what we are interested in. It's returning an address to index 0. So if I want, and I go ahead and say, okay, I want to create an integer pointer and assign it to malloc. Say malloc 4. What this is going to do is that this malloc, in the first place, is going into my heap to go and create 4 bytes of space for me. Okay, so we'll have something of this one: 0, 1, 2, 3. Please, I hope people are not counting this one as parts. We are starting counting from 0. So this is the first byte, second byte, third byte, fourth byte. But these are indices. That's why I have 0, 1, 2, 3. Okay, it is first going to create this space. Once it creates that space, each of these has its own address. Each of these has its own address. But this malloc is a function that is returning to us the address to this particular one, the 0 index or index 0. malloc returns the address to index 0. Okay. So here, what we are doing essentially is that we have initialized a pointer p, and this pointer p is equal to the address of this particular location. And once we have that specific address, using pointer arithmetic, we can get access to the subsequent ones. Okay? Because you should know that addresses are just numbers, just like room numbers. From room 10, you go to room 11. From room 11, you go to room 12, 13, in that same way. So if I tell you that, okay, you sent me to the hotel to book a room. So when I went, you told me that there are 4 people coming. So I booked 4 rooms, and those 4 rooms, they are in the order, in the same order. I mean, they follow each other. If I come and tell you this information, what do you need from me? What is the address or the room number for the first room? So far as you get the room number for the first room, you won't get lost section for the rest of the 3 rooms. And I hope that makes sense. So all you need is the address to the very first element. Once you have address to the first element, you can then always jump on to the other element. If I want the next one, it's just +1 to go to the next room. If I want the next 2, it's just what, +2 to go to that specific room. Okay, so that is how we end up passing the outcome of malloc to the pointer that we have created. Reason being that it returns what, an address. Any questions? Any questions? Yes.
Thank you, Doctor.
Yeah, welcome.
My question is, to avoid lagging, where should we store our function? Should we store it in dynamic memory or the fixed one, which is static?
Okay. So just as I said earlier, when it comes to using the stack memory or the static memory for that matter, you do not really control it. Okay, so your program, no matter what you do, so far as you have a function in there, like main at least, and you know that you don't have a C program without a main function. So definitely that stack memory is going to be used in one way or the other. So you don't control much of it. And you can have your programs running with a stack. You can decide to write a program that doesn't use heap. The heap comes in at a point. So this, whatever you are talking about, is this something that you want to be able to manipulate? Okay, so now we are going to learn about struct. So we realize that to keep data, that will help us do much. We are either using arrays or we are using struct. So with your arrays and your structs, you want to be able to manipulate. So if you are going to be able to manipulate those ones, then you have to do it in the heap memory and not the stack. It's not going to happen in the stack. But the ones that you don't need to manipulate. So if you want to create an array, predefined array or an array with a predefined size, you are not going to change it along the line or anything, then you don't need to even bother yourself going into the heap, because then the computer will take care of it as and when it's needed. But if it is something that you are going to make changes to along the line in your program, okay, I'm going to be adding, I'm going to be increasing the size of my array, I'm going to be decreasing the size of my array, then I should use heap. So that is what should guide you. Are you going to be manipulating this or not? If you are going to be manipulating it, then use heap. If you don't want to manipulate it, then you can use the static memory or stack. Yes. Chiquito. I thought you were going to say something.
No. That was an error. No. Sorry.
Okay. All right, sure. Yes, any other questions? Okay, then let's continue. So we are still talking about dynamic memory allocation. Dynamic memory allocation. And we've mentioned that we are in our heap. And we've mentioned malloc. And we said that malloc retains address to the very first room. Usually I like to use that hotel analogy. So address to the very first element or what we will call index 0. At least just remember this all the time. This is what we are doing. If you are doing dynamic memory allocation, this is where you are using the heap, and we are calling malloc. Malloc is always going to retain the first one. So even if I do malloc 100, it's still going to retain just address of the first element. That's all. Okay. And from the prototype of malloc, you realize that it retains a void pointer. Okay. Void pointer in the sense that where it is pointing to or what it has created. We have learned that anytime you are going to use a memory or you are talking about size, you are looking at what type of data is being stored there. But malloc doesn't consider specifically, like it doesn't tell. In fact, it's just space that it's going to create. It hasn't put anything there. So you are the one who is eventually going to decide that, okay, it is a set of characters that I want to store there, or it is a set of integers that I'm going to be storing in that space. Okay, so for malloc, it doesn't tell us that specific data type. For that matter, we say it returns a void pointer. Okay, that is why we have its prototype looking like this. But then, once we know that it is not returning a pointer to a specific data type, it means we can assign any data type at all that we want to it. So how can we do that? One of the ways that we do that is through what we call type casting. So you can cast one type to the other. Okay, so for instance, let's say I already gave you a character. You can force the character to behave like an integer. And that is what we term type casting. So even though you were initially an integer, now from here onwards, I'm going to use you as a character. That is if I typecast you to character. Okay, so in the same way, we can typecast the outcome of a malloc function to any data type of our choice. So for instance, even though we know it's going to retain this is how you typecast something. So just put the name of the data type. So in this our case, we want the pointer that is returning should point to an integer. Okay, so we do this just by writing integer, then asterisk or in brackets before the malloc. Then the size, say 10. Once you have done this, what you have done is you have forced malloc to create a space and told the computer that this space that I have created is going to only store what? Integers. So that is typecasting. Once you have put this in front of malloc, you have forced it. So after creating this space, you can go ahead and put characters in there. Without the typecasting, when you create the space, you can put anything that you want in there. But as soon as you typecast it to something, so you have decided that forcefully, this should only contain this type of data. So by typecasting it to an integer, we have to only put integers there. But eventually, whatever happens, you know that in C, you always have to declare data type. So whether you typecast or you don't typecast, at the end of the day, the pointer that you are going to use, before you use it, you still have to give it a particular data type. Okay. So as it stands now, the typecasting isn't that much importance, except that when you use some compilers, they'll give you an error if you didn't typecast it. Okay, so depending on the compiler that you are using, you may have to typecast or not. And you should understand, at least you should understand what a typecast is, why you do it, and so that if you are getting an error from a compiler, you should know why that error is coming and what you should do. So always remember, if you append character series before malloc, say malloc 5, then all you are saying is that make room for a space of 5 bytes inside the heap memory, and that space is going to be used to store just characters. One thing about this, about the dynamic memory, is that now that we have decided, so let's assume I did this, then a pointer to say A is equal to then malloc of 12. Once I have done this, all that we are saying is that this particular pointer will end up pointing to the address of the first member of those 12 spaces, 12 bytes that this malloc is going to create. Okay. But there are things that even before you write your malloc function, you don't know the exact size. This one that I'm putting in here, 12. What if I don't know the exact size of the data that I'm going to store in that memory? So there are cases like that. And once I don't know the exact size, it has been made flexible for me to do some form of a calculation to get that size. And the reason why this calculation is important is that, well, you are working on your computer and you have decided that you are going to be working with, say, integers. And for your integers, you have each integer to be taking up 4 bytes. But remember that that is unique to your particular computer and compiler that you are using. So even though your integer is giving you 4 bytes, somebody can go and run the same program on a different computer, on probably a different compiler, and they will end up getting integer to be 2 bytes. So you are getting the size of an integer to be 4 bytes. Someone else runs your program and gets the size of an integer to be 2 bytes. So if you allocated space for 3 integers, and for that matter, you did your calculation 12 here, when this person runs the program, you realize that they are getting 6 bytes rather. So you are misusing your memory. Very bad. Very, very bad. So always we are looking at efficiency. We should have our program use the memory efficiently, because other programs as well need to use the same memory. So you can't just be wasting memory like that. Say, oh, I mean, this one is just 6 bytes. I have more. I have 4 gig, so I can just play around. No. You have to always make sure you are using the memory efficiently. For that matter, it's not advisable for us to just go ahead and do our own calculation and put it there. Let's make it dynamic. Let's make it flexible. Okay, so how do we make it flexible? Since we got the 12 by saying that an integer is 4 bytes and we are storing 3 integers, then it means we can equally go ahead and say 3 times, then we'll use the size of function. Okay, size of, then we pass this, it is an integer we are looking for, size of integer, then we multiply the outcome by 3. This tells us that, oh, malloc, go and create. So in essence, we are going to have something like this. And it tells us that malloc, go and create enough space to contain 3 integers. So this computer that you are using, you malloc will go and check what is the size of an integer on this computer. If the size of an integer on this computer is 2 bytes, then what I'm telling you to do is reserve 3 times 2 bytes space. That is 6 bytes. But if malloc goes in and finds out that the size of an integer on this specific computer is 4 bytes, then it ends up reserving 3 times 4 bytes, which is 12 bytes. So there is that flexibility. Okay, so this is the preferred way of using malloc. Always think about the size that you want to create. Is it an integer? Whatever you are going to be storing there, what is it? Is it an integer? Is it a character? Is it a float? Is it a double? Is it a pointer? What are you going to store in that space that you have? Once you know what you are going to store in that space, then use the size of function on that particular data type, multiply it by the total number. So if I want to store, say, 10 characters, instead of in my head saying, oh, character, for every character, it takes up just 1 byte. So let me go ahead and store 1 byte. No, I may be wrong. So what I'll have to do is maybe declare my character pointer, say pointer to A, and assign malloc. Then instead of writing my own stuff in here, I'll now do 10 times then size of character. So this has made it dynamic enough. Okay, that means that this will check for the computer that you are using, the compiler that you use to compile the program, and check its size before it comes to multiply it by this and allocate the space that is exactly needed. Any questions so far? Any questions? Okay, so the next set of things that we should know is, so far as we have executed this, if the very first time you execute it, you have created space in that heap memory that we talked about. So this is what is happening. You have created this space, okay? And the address here, I think I should illustrate this better. All right, so I just pray please pay particular attention here. In your program, okay, let me start asking questions. Today I haven't asked anyone a question. Let me ask some few questions. If I have a program and I have, let's say in my main function, in main, I have variables defined, let's say A as an integer is equal to say 10. Then I also have an integer pointer declared, pointer to A. Okay. So the question here is, which part of my computer's memory will A be stored? Which part of the memory will A be stored?
The stack.
The stack memory. Thank you.
Yes.
Okay, so we'll have, I'm not going to draw everything. So let's assume this is the stack memory. Okay, the very first thing that's going to happen is we are going to create the main frame. So a frame for main. Then inside the main, we now have this variable A is equal to 10 stored here. What about the pointer? Where will that also be stored?
Now it goes to heap.
That will go to heap. Do you all agree?
It will be on the stack.
Okay. Any other? Let me hear. Yes. What do you say? The pointer, is it going to stack or heap? In fact, everyone should suggest something.
To go to the heap.
Okay, you must say it goes to the heap. Yes.
Stack.
There are a lot of you. Okay, Mary says stack. Yes. All right, so let's continue. Thank you for your submissions. So what is actually happening is that this pointer that we are creating is still a variable. If you remember that the pointer in itself is a variable, just that it stores the information it stores is just an address, but it's a variable. And so far as it's within main function here, you haven't created anything in the heap. I've told you we only enter the heap when we have on our own created something that, hey, go to the heap. Until we do that, we've not entered the heap. So this will also be stored here as PTA like that inside the main frame because it's a local variable within main. I hope it makes sense. We can't jump to heap because we have not allocated any space in heap. Okay? Then the tricky part for which I came back here for you to see what actually happens is that if now I go ahead and say PTA is equal to malloc, say malloc 5. Now, it's a bit tricky, but let's see, where do you think, like what's going to happen in terms of the memory? Are we now going to move PTA from stack and put it at heap, or is it still going to remain at stack? And what is going to happen in our heap? Yes.
It will still be on the stack, but then you will have created a memory block in the heap.
Okay. So what he said is that we would have created a memory block in the heap, but this will still remain in the stack. Let me hear from Alex. What do you also think?
I agree with him.
I agree with him. That pointer will pointing to the memory in the heap.
Okay. All right. Thank you all so much. So what you should remember is this. I said when you use the malloc will go into the heap and create. So this is 5. So it's going to create that 5 bytes of space. Okay. But what is it going to return? It's just going to return an address of the very first one. So all we are doing here is that, oh, this PTA is already in the stack as a variable, except that we have not assigned a value to it. And to assign a value to a pointer, that value has to be what? An address. So the address to this particular thing will now be returned. So assuming the address is something like this, say 84, something like that, we will now say this is the value of PTA. So PTA here will now be assigned to that. Okay, but this memory has been created. And this is the address, or this is the pointer to it. So if I want to have access to any of these, I'll come and use pointer A. I know pointer A, you apply to this. So if I dereference you, then I should get the value in the first space here. If I should go to the next one using pointer arithmetic, I think our next session will do more of that. We'll be able to access the next one, okay? But what you shouldn't forget is the fact that you don't move this pointer and come and put it here. No, it's a pointer. And if it is a pointer, it can stay where it is and store the address to anything. So remember that when we are dealing with a heap, it's always a pointer to it. So it's like we don't enter it ourselves. We just use a pointer. Oh, I have the address to this location in the heap. I have the address to this location. So inside our stack, we can always get the address to something in the heap. I hope that makes sense. So in this specific case, let me take it again. what we have done is that initially we had our main function, and what we've said so far is that functions and local variables are stored in the stack memory. So that means that your program, as soon as it saw the main function, created a frame for the main function. So we have it inside the stack memory as main. Then inside the main function, there was an integer declared as A, and an integer variable declared as A. So A will be stored here. There was another integer variable, but this time around it is a pointer, and it's declared as PTA. So your computer will still have PTA in here. Okay, so if you go ahead and create something inside the heap, a block of memory inside the heap, and you decide to pass the address of the very first element, so in the 0, the address in the 0, decide to pass it to this, then all that you have done is just giving a value to this. So we are still inside the main. But when I ask you, where does this point to? You know that it points to this. Okay, so in another example, similar example, if I have, say, our main function, and inside main we have integer A is equal to 10. Then I have integer pointer PTA is equal to address of A. Then integer pointer PTB. With this, someone should just unmute and tell us. Memory allocation, what do we expect for this? Yes, there is a main function that contains these declarations. So share with us the memory allocations. How is it going to be allocated in the memory of your computer? For anyone, guys.
B is still going to be allocated inside main.
Okay, so everything here, A, PTA, PTB, will be allocated inside the frame that has been allocated for main. So let's assume these ones didn't exist initially. So we have A here, we have PTA, this will grow to contain PTB. Okay, maybe I shouldn't have used the word grow, but I mean, before you even do it, it would have, it knows these things are there. Like, these are the things that I'm going to need. Okay, so that's why I said there's space for it inside the main. So PTB and PTA. Okay, now we have assigned a value to this. We have also assigned a value that's an address to A, to this. But PTB hasn't got a value yet. So if we go ahead and do, how is it called, malloc, say our PTB is equal to malloc of 2. All that would have done is that would have created space, 2 bytes of space here, and pass the address to in the 0 to B. So B will still be at where it is, except that now it is carrying an address, and that address points to the heap. But A carries an address that points to A. So you realize that the pointer can point to any of them, depending on how you assign the value you assign it. The pointer can point to a memory location inside a heap or inside a stack. It depends on how you point it. But always remember, malloc will return a pointer. And I was saying earlier, as soon as you do this declaration here, this thing here, you have created this space. And until you go ahead to free it, that space has been created and cannot be used by any other program. If you do not use it, that space has been taken up. So you have reserved these 2 bytes. So for those of you who have been using your phones to do malloc, and you have reserved space, and you didn't free your space, it's going to be used until maybe you take, like, it's going to be like it has been captured until you power off and power on your phone. That's what is happening. So if right now I try and I go and allocate space, malloc space of say 4 gig on my computer right now, and I don't free it, you see what is going to happen. It's going to take up that enough space, and until the computer is powered on again, that space is going to be unused and unallocated to anything unless I decide to use it. Okay? So the next important thing, I think time is up, we have to go for ALD, but the next important thing is that you have to free this. You have to free this memory location. Okay, so that is when we use the free function. The free function is what we use to free the memory location. Okay, then as I mentioned earlier, there is also calloc and there is realloc. But let's see, I don't know when, but we'll communicate in the group, okay? So the next session, I'll try my best to get some of the tasks that we did on malloc and bring it so that we'll discuss those ones. We'll take it practically, how you do this, why we do that, so that you see. But the goal for today's session was for you to understand the dynamic memory allocation and how it comes by. So any questions before we end this session?
You can quickly help us, tell us little about the free, so that we will know that we have completed how we allocate memory and how to free it.
Okay, so with free, all that you have done is here, after you have created your malloc, you assign it to this. Okay, so if you call free ptb, that is all you need. What did you allocate your memory to? Once we know that, oh, I allocated the malloc, I allocated this memory to this, okay, or I assigned that memory to this particular variable or special variable in that sense, that's a pointer, then I apply the free on the pointer, and that is going to make the memory available. So like the computer understands. As soon as you do that, the computer understands that, oh, this memory that was reserved now is available. I can use it for anything. So if there is another program, that address that you took, it does not, it no longer belongs to you. So any other program that you are running can use that same address. But until you did the free, no other program can use that address. So the address that you have assigned, that is, remember that when you do the malloc, it's not just this space that it stores. It lists a total number of bytes that you passed, and each of them has its address. So it means that all those addresses, it's like going to the hotel. When you went to the hotel and booked 4 rooms that are continuous, and they told you that the first room was room 101, and you know that you booked 4 rooms, so that means you booked 101, 102, 103, 104. So until you come to the receptionist and tell the receptionist that I want to check out. I want to check out. So if I come and check out room 101, you should know that I was the one who collected all those 4 rooms. So at the end of the day, now I have left all those 4 rooms. You can use them. So that's how we use the free. Once you apply whatever you assign malloc to inside free, then the computer understands that now that various address locations are available for you, so they can equally go and use it. Any other question?
Do we need to declare it one by one, or we can make use of comma or a semicolon and put everything in a parenthesis?
For the free various spaces that was given, is that it?
Yes, sir. Yes, sir.
Is it that maybe when I ran malloc, I said malloc allocated 3 bytes? So are you asking that we should free like the first one, the second one, the third one? Is that a question?
And like if we have more than one malloc like this, like malloc
Oh,
3,
okay.
if we have more than it.
Okay, so that means that you are saying if we had malloc say 4 assigned to, let's say, A, I'm just using this, and B is malloc 5. Is that what you're saying? Something like this?
Yes, yes, sir. Yes.
And you're asking if we can do free A, comma B, something like this.
Yes. Or do we need to declare it free A, free B, you know?
Okay, yes. So for what I know now, you would have to declare free A, free B. Okay, I haven't tried this before, and it's a function. Okay, and the function understands its argument. So depending on the prototype that was written for free, it may not take this, but I've not tried it. We'll have to try it. Probably during our next session, we'll try that and see if it works.
Okay, sir. Thank you, sir.
Right. You're welcome. All right, so if there is no other question, then we have to break and go for AMA. Let's go and learn from there as well. And hopefully I don't know, but I hope we'll do that as soon as we can, the practical part, so that we can move on to the next set of stuff that we are currently doing. So thank you all for coming, and I'll see you in the next session. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Thank you.
Bye.